into the detail of how to use the Biot-Savart law. So the easiest one to use is a wire. Let's say I have a wire, and it has a certain length, let's say L, and let's say I want to find the magnetic field at the midpoint. Okay? Or I could do any point, really. It turns out that for magnetic field, the integral is doable no matter what point you pick, right? So if I want to, let's say I want to just some arbitrary point. So let's put my coordinate axis like this, x, y, and then I could say the total length is L, and then I could pick here a general point, A, B, right? And I want to find the magnetic field right there at AB. So what I do is I take a little piece of the current is flowing this way. This is the I. So let's say the current is flowing to the right. So I take a little piece, and that's my dl vector. dl is the little vector, and it's pointing to the right. In other words, the dl vector points in the same direction as the current flow. The r hat vector is a unit vector, so it has no magnitude. It's unit vector pointing towards the point. Okay, so this is dl, the one down here. The r hat vector points towards that point. All right, so you take the cross product of that. So when you take the cross product of dl and r hat, direction-wise, what direction does that give you? dl cross into r hat is out of the board. That means the magnetic field at that point is out of the board. As a matter of fact, any point here is still out. dl r hat, still out. So over here, any point along here, the magnetic field is out of the board. How about the magnetic field right here? Well, dl will be like this. R hat will be like that. The cross product of dl and r hat is 0. They're parallel. So that means the magnetic field equals 0 along the wire this way, along the wire this way. Right? How about the magnetic field down here, in any point here? So dl will be like that, and then r hat will be down, right? Because it's facing towards the point. So dl cross into r hat into the board. So if the current is flowing that way, it creates a magnetic field that loops around the wire. It comes out of the board, loops around, goes in. So it kind of looks like this three-dimensionally. There's another way to do this. There's another right-hand rule besides the dl crossing r hat. You can do this way. I'm going to show you the other right-hand rule. Put your thumb in the direction of the current flow and just curl your 4 fingers around, you see? So that means this here, the magnetic field is going to go into the board, then out of the board, right there. So you can either use the dl into the cross into r hat method, or the curl your 4 fingers around the current. So if the current was going this way, then it would go into the board, out of the board. Into the board, out of the board. It would be opposite, you see? Okay, so direction-wise, now we determined that it's out of the board. How about the magnitude? The magnitude of dB is mu 0 I over 4 pi the magnitude of r, which is 1, the magnitude of dl, which is just dl, times sine of the angle between them, over r squared. Okay? Now dl in this case is just the same as dx, right? It's just dx. Sine of theta is what? Let's redraw it here a little carefully. So here is the thing, the wire. Here's my point. This is dx. This is x. This is the arbitrary point A, B. So the distance here, this is the angle, right? Sine of that angle is, this is B. And then this distance right here is B minus x, right? No, I mean A minus x. Because A is the x component of that point. So A minus x, so this distance is going to be A minus x quantity squared plus B squared. Okay? So sine of the angle is going to be B divided by square root of A minus x quantity squared plus B squared. That's the sine of the angle. But then you got r squared, which is this one also. This is this one is r. That's the distance from here to there. So r squared is equal to this whole thing, right? So my final integral is going to be like this. B total is going to be, this is constant, mu 0 I B over 4 pi dx over integral A minus x quantity squared plus B squared to the power of what? I have a complete number 1 and then the power of 1/2. So that's power 3/2. Integral from 0 to L. Okay? Now, if there's no numbers, then we got to do an indefinite integral. If there were numbers given in the problem, then we could do a definite one. This one is just a general variable, so we're going to have to do an indefinite integral. Okay? What's the integral of that? 3/2. That one is probably... Is there one available? Let me see. Let me go get a calculus book. See if that's...
You can choose any one you want, actually. So that is a possibility. So from this choice, you get this wave of pi.
Okay, good.
Okay, so, but... yeah, so that is a possibility. Any wavelength.
Yeah, this one is one of the forms here. Have we seen this integral before in chapter 23? Did this ever appear? 3/2? I think so, yeah. When we were doing the electric field, it was kq over r squared, and then we had to use symmetry. So that's where cosine or sine came in, right? So I believe the same integral came in chapter 23 because we had to use symmetry, right? So the integral is equal to x over, it's going to be b squared. And then the bottom is going to have square root of one half power from 0 to L.